In a world filled with questions, where wisdom knows no boundaries, join us on a journey of enlightenment and endless learning. Eternal Teachings. TV. Discover the eternal.
Milankovitch cycles, Earth's orbital dance and its impact on climate. The Milankovitch cycles, named after Serbian geophysicist Milutin Milankovitch, describe the collective effects of changes in Earth's movements on its climate over long periods. These cycles, driven by variations in Earth's orbit and rotation, significantly influence the distribution of solar radiation reaching our planet. This variation in solar energy, in turn, plays a crucial role in driving Earth's climate patterns, including the occurrence of ice ages and warmer interglacial periods. The three components of Milankovitch cycles. 1. Eccentricity, or the shape of Earth's orbit. Earth's orbit around the Sun is not perfectly circular, but rather slightly elliptical. The degree of ellipticity, or eccentricity, varies over a cycle of approximately 100,000 years. When the orbit is more elliptical, the difference in solar radiation received between Earth's closest and farthest points from the Sun, perihelion and aphelion, is greater. This can lead to more extreme seasonal variations. 2. Obliquity, or the tilt of Earth's axis. Earth's axis is currently tilted at approximately 23.44 degrees, but this angle varies between 22.1 and 24.5 degrees over a cycle of roughly 41,000 years. Changes in obliquity affect the intensity of the seasons. A greater tilt leads to more extreme seasons, with warmer summers and colder winters. 3. Precession, or the wobble of Earth's axis. Earth's axis wobbles like a spinning top, completing a full cycle of precession every 26,000 years. This wobble affects the timing of the seasons relative to Earth's position in its orbit. It can cause the northern hemisphere summer to occur when Earth is farthest from the Sun, leading to milder summers and vice versa. How Milankovitch cycles influence climate. These three cycles interact in complex ways to influence the amount and distribution of solar radiation reaching Earth. When these cycles align to favor increased solar radiation in the northern hemisphere summer, it can trigger a warming trend that melts ice sheets and glaciers, leading to interglacial periods. Conversely, when conditions favor reduced solar radiation in the northern hemisphere summer, it can promote the growth of ice sheets, triggering an ice age. Evidence for Milankovitch cycles. The evidence for Milankovitch cycles comes from various sources, including ice core records. Ice cores extracted from glaciers and ice sheets provide a detailed record of past climate conditions. These records show a clear correlation between variations in Earth's orbital parameters and changes in temperature, greenhouse gas concentrations, and ice volume. Sedimentary records. Ocean and lake sediments contain layers that reflect past climate conditions. Analysis of these layers reveals cyclical patterns that match the timing of Milankovitch cycles. Astronomical calculations. Scientists can calculate the past and future variations in Earth's orbital parameters with high accuracy, allowing them to model the impact of these cycles on climate. Understanding Milankovitch cycles is crucial for several reasons. First, they help scientists reconstruct past climate conditions and understand the natural variability of Earth's climate system. Second, Milankovitch cycles provide a framework for incorporating orbital forcing into climate models, which improves their accuracy in simulating past and future climate changes. And finally, while Milankovitch cycles operate on long timescales, understanding their influence can help scientists refine projections of future climate trends. The Milankovitch cycles are a fundamental driver of Earth's climate variability. These cycles, driven by variations in Earth's orbit and rotation, significantly influence the distribution of solar radiation reaching our planet. This variation in solar energy, in turn, plays a crucial role in driving Earth's climate patterns, including the occurrence of ice ages and warmer interglacial periods. By studying these cycles and their impacts, scientists can gain valuable insights into the natural rhythms of Earth's climate system and improve their ability to predict future climate changes. The Milankovitch cycles, as previously discussed, play a pivotal role in shaping Earth's climate over long periods. Their influence extends to dramatic shifts in regional climates, as evidenced by the transformation of the Sahara Desert from a lush, green landscape to the arid expanse we know today. This transformation, driven by variations in Earth's orbital parameters, provides a compelling example of how Milankovitch cycles can profoundly alter climate geography. The Green Sahara, a glimpse into the past. Geological and archaeological evidence reveals that the Sahara Desert was not always a barren wasteland. In fact, during several periods in the past, known as African humid periods, the Sahara experienced a much wetter climate characterized by increased rainfall, expanded lakes, and flourishing vegetation. These periods, which occurred roughly every 20,000 years, coincided with specific configurations of the Milankovitch cycles that favored increased summer insolation or solar radiation in the northern hemisphere. How Milankovitch cycles greened the Sahara. The primary driver of the Green Sahara phenomenon was the precession of Earth's axis. When the northern hemisphere summer coincided with Earth's closest approach to the Sun, known as perihelion, it received a greater amount of solar radiation. This increased insolation intensified the West African monsoon, a seasonal wind pattern that brings moisture from the Atlantic Ocean into the Sahara. The strengthened monsoon led to increased rainfall, triggering a cascade of effects that transformed the desert landscape. Increased rainfall. The intensified monsoon brought abundant rainfall to the Sahara, significantly increasing the availability of water for plants and animals. Expanded lakes and rivers. The increased rainfall filled depressions and basins, creating vast lakes and flowing rivers across the Sahara. Lake Chad, for example, expanded to an area larger than the Caspian Sea during some Green Sahara periods. Flourishing vegetation. The availability of water and a more humid climate supported the growth of lush vegetation, including grasslands, shrubs, and even trees. Fossil pollen records from the Sahara reveal a diverse array of plant species that thrived during these periods. Diverse fauna. The flourishing vegetation provided habitat for a wide range of animals, including large herbivores like elephants, giraffes, and hippopotamuses, as well as predators like lions and hyenas. Rock art found in the Sahara depicts scenes of hunting and fishing, further attesting to the rich biodiversity that once existed in this region. The end of the Green Sahara. The Green Sahara periods were not permanent. As the precession cycle continued, the Northern Hemisphere summer gradually shifted away from perihelion, leading to a weakening of the West African monsoon and a decrease in rainfall. The lush landscape gradually dried out, lakes and rivers evaporated, and vegetation dwindled. Over time, the Sahara reverted to its arid state, leaving behind only remnants of its past greenery in the form of fossilized pollen, ancient riverbeds, and rock art. The legacy of the Green Sahara. The legacy of the Green Sahara extends beyond its geological and ecological impacts. The cyclical shifts between wet and dry periods played a significant role in shaping human migration and cultural development in the region. During the Green Sahara periods, the abundant resources attracted human populations who settled in the area and developed unique cultural practices. As the Sahara dried out, these populations were forced to migrate, contributing to the spread of agriculture and other technologies throughout Africa and beyond. Implications for the future. The study of past green Sahara periods provides valuable insights into the potential future impacts of climate change. As the Earth's climate continues to warm, some regions may experience increased rainfall and vegetation growth, similar to what occurred in the Sahara during the African humid periods. However, other regions may face desertification and water scarcity. Understanding the complex interactions between Milankovitch cycles and regional climate patterns is crucial for predicting and mitigating the potential consequences of future climate change. Conclusion. The Milankovitch cycles have played a profound role in shaping Earth's climate geography, as evidenced by the transformation of the Sahara Desert from a green oasis to an arid wasteland. This transformation, driven by variations in Earth's orbital parameters, highlights the intricate relationship between astronomical cycles and regional climate patterns. By studying these cycles and their impacts, scientists can gain valuable insights into the natural variability of Earth's climate system and improve their ability to predict and adapt to future climate changes.